Hello, Matthews Gatos here. In this video, we're going to cover the fundamental counting principle. Let's get started with an example. So I want to start with a tree diagram just to illustrate how the fundamental counting principle works. So imagine I have 3 coins and I'm going to toss these coins. I want to list all the possible outcomes. So we start with coin 1. Now with coin 1, we have a possibility of flipping the coin and it landing on heads or tails. So I flip coin 1, and then coin 2, if I get heads on the first toss, coin 2 could also be heads or tails. And if I get tails on the first coin, I could still get heads or tails on the second coin. Coin 3 also branches out into 2 as well. So for each one of these options, coin 3 branches out into heads or tails for each one of the options. So as we go along the tree diagram, every coin I have branches out 2 more times. So reading all the outcomes, I can have heads, 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 or heads, heads, tails, and I just read along the branches of this tree diagram to come up with all the possible outcomes. Now, that wasn't so bad because it was only 3 coins, but imagine if I asked you to list out the outcomes for 20 coin tosses. That would be a lot. So in 30-1, sometimes we don't want to know what the specific outcomes are. We just want to know how many outcomes there are. So for example, we know that these were all the outcomes that we just came up with, but in 30-1, we just want to know how many outcomes are there. And in this case, there were 8. So now that you've seen us listing out the outcomes, I want to figure out how could I just know it was 8 outcomes without listing them out. And this is where the fundamental counting principle comes in. Fundamental counting principle says if there are m ways to do one task, n ways to do another, and so on, you multiply all those tasks together to figure out how many outcomes there are all together. So let's go back to that coin example. Now we know it had 8 outcomes, but here's why. Because coin 1 has 2 possibilities, heads or tails. Coin 2 has 2 possibilities, heads or tails. Coin 3 has 2 possibilities, heads or tails. When I multiply those together, I get 8 outcomes. Now the reason that we're multiplying the choices together is because there's the word and. How many outcomes of tossing coin 1 and coin 2 and coin 3? And in math means multiply. So now that we know that the fundamental counting principle works, why it works, let's try some examples. So in this one here, I have an aircraft. So it's a plan, like a map of the aircraft. There's 33 seats that are taken. Those are the ones that are shaded in. And there are 17 seats available. Now let's say we have 6 customers in line and they want to buy a ticket to be on this plane. I want to know the number of ways they could be assigned to a seat. So 6 customers, 17 seats available. So the first customer comes up to the desk and they have a choice of any 17 seats. They select a seat and then customer 2 comes up. Now they can't choose the seat that customer 1 chose, so they actually have 16 choices. It goes down by 1. Customer 3 can't choose the seat of customer 1 or 2, so they have 15 choices, and it goes down by 1 each time. So I multiply these together because it's and. How many choices for the first customer and the second and the third, so on. So to find out the number of ways they could be assigned a seat, I just multiply that together and I get that my answer is 8,910,720 ways. Now I wouldn't want to list all those ways out, but at least we now know how many ways there are. Let's try another one. So in this one, I want to know how many 4-digit odd numbers without repeats there are. So before I do this question, I have 2 questions to start with. First of all, can a 4-digit number start with a 0? So imagine if I started with a 0, for example, 0, 1, 2, 3. Is that a 4-digit number? Well, hopefully you say no, because that, if it starts with a 0, is actually a 3-digit number. So I have an implied restriction that a 4-digit number, or actually any greater digit than 2, 2-digit, 3-digit, 4-digit, etc., can't start with 0. Now we had another restriction there that it had to be an odd number. So what makes a number odd is the last digit. So the last digit must be an odd digit. Only the last one has to be odd to make the whole number odd. So now that we know those 2 restrictions, let's go ahead and figure this out. So fundamental counting principle, the key really to me is labeling each of these stages. So I start with that the number has to be odd, which means it has to end in an odd digit, 1, 3, 5, 7, or 9. I have 5 choices there. Now, it's a 4-digit number without repeats. So we established it can't start with 0, but because there's no repeats, it also can't be the last. So we have 10 digits to choose from, but I have 2 limits or restrictions. So 10 take away 2 means I have 8 choices. For this next one, I have 10 digits to choose from. I can't have the first or the last, 2 restrictions, and it's 8. Now, the reason it's 8 again, because you would think it goes down by 1, is that 0 goes back into the mix. Okay, and then for the third digit, it can be any of the 10 digits except the first, second, and last, because repeats aren't allowed. So 3 restrictions mean that there are 7 choices. So multiply all those together and you have 2,240 4-digit odd numbers without repeats. So my tip for you in this question is the number of choices for each stage is the total number of choices available to you. Take away the number of restrictions. Let's try another one. So I want to know how many 4-digit bank codes have at least 3 threes in them. So this word at least 3 means a minimum. So if I'm talking about a 4-digit bank code, it could be 3 threes or 4 threes. And at least means we have cases. Now, in terms of passwords, PINs, can PINs begin with 0? They can. So PINs can begin with 0. It's different than a number because this is just 4 digits that you're plugging in. So PINs can begin with 0. So we're going to have cases and we are going to add the cases together because of that word or. So I can have 3 threes or 4 threes. So when we have at least and at most, which we'll see later, questions always have 2 different cases, 3 different cases, etc., and we add those cases together. So let's look at the first case of having 3 threes. So 3 threes, so I have 1 choice, it's a 3, it's a 3, it's a 3. And because there's 4 digits, I have something that is not a 3. If that was a 3, it would be 4 threes, but I want 3 threes. So there are 9 numbers that are not 3. But nobody said that the non-3 digit is in the last. It could be in the second last position. It could be in the second position, or it could be in the first position. Now, each one of those would have the same calculation. We're just shifting the 9 around. So really what we have altogether is 9 options for 3 threes multiplied by the 4 places that the non-3 digit can be in, which means I have 36 ways I can have 3 threes. Now, 9 ways again to have the 3 threes multiplied by 4 positions of the non-3 digit. So 36 different passcodes that have 3 threes. We also have to now consider what happens when we have 4 threes. So 4 threes, this would be a very unsafe password. I don't recommend this one. It would be 3, 3, 3, and 3. So really only 1 choice for each one of those. So 36 ways to have a 4-digit PIN with 3 threes, 1 way to have a 4-digit PIN with 4 threes. So altogether, 37 possible 4-digit bank PINs with at least 3 threes. Okay, in our last example, we're going to run through a couple scenarios for this one question. So I want you to imagine that we have 5 people standing in line. Alice, Bob, Kathy, Don, and Edward. They're going to line up for a picture, and I'm going to throw a couple of restrictions at you for each of these scenarios. Okay, so in the first one here, I have Alice and Bob want to be on the ends, but it doesn't specify what end they need to be on. So they could be grouped together at the front. There would be 2 choices there, either Alice or Bob, and then whoever is in the front, there's only 1 choice for the back. Because if Alice is in the front, Bob has to be in the back. If Bob is in the front, Alice has to be in the back. And then we have 3 people left to arrange in the middle. So we have Kathy, Don, and Edward. So 3 choices, 2 choices, and 1 choice. So I just have to multiply those together. 2 times 3, 6, times 2, 12, times 1 and 1 is still just 12. So 12 different ways of 5 people lining up where Alice and Bob have to be on the ends. So my tip here, always focus on your restrictions first. Okay, let's look at a twist on this question now. It's going to be all about Alice and Bob. They're just so difficult. So Alice and Bob in the next case, let's say they want to sit together. Okay, anytime you have a together question, what I want you to do for these questions is I want you to group and then arrange. So since Alice and Bob must sit together, let's first group Alice and Bob as though they were one person. So grouping Alice and Bob together could be Alice, Bob, or Bob and Alice. So there are 2 ways to group Alice and Bob together. Okay, and then we get into the arrange part. So for the arrange part, what I want to do is I want to have Alice and Bob together plus the 3 others. So all together, that's really 4 people that I have to arrange. So 4 people to arrange, there are 4 choices for first, 3 choices for second, 2 choices for third, 1 choice for fourth. So all together, I just multiply that together, and I'm going to get that there are 48 ways for Alice and Bob to be together. So again, for these types of questions, I want you to group and then arrange. In my last question, I want to look at how many ways can Alice and Bob sit separate. In other words, not together. There are so many cases. I wouldn't even want to list all the cases out. I have a little illustration here so you can just see some of the cases. So if Alice sits in the first position, Bob can't be in the second. If Alice sits in the second, Bob can't be in the first or the third, and so on and so on. There are way too many cases to consider. So what we're going to look at is the 2 possibilities. Either they're together or they're not together. Well, we already figured out how many ways they are together. So to figure out how many ways they're not together, I'm going to do all the arrangements with no restrictions, subtract the ways it can happen, the ways they're together, and that will equal the ways it can't. So I want you to stay positive. Never solve a negative or a can't question. So all the ways with no restriction would be all the ways that I can arrange 5 people, which is 5 times 4 times 3 times 2 times 1. So that's 20, 60, 120 ways to arrange 5 people in line. Now we already know how many ways Alice and Bob can be kept together because we just calculated that in part B. That's 48. So to figure out the ways that they're not together, you just have to do 120, take away 48, which is 72. So this is a great example for fundamental counting principle where we always want to keep it positive. So you've seen a bunch of examples with fundamental counting principle. I want to go back to those odd numbers because you know what really seems odd to me? What really seems odd to me is numbers that are not divisible by 2. Isn't that odd to you as well? I hope that this video helped. If it did, give it a thumbs up so we can help more mathies, and hit subscribe as well. Thanks for watching, and I'll see you for the next one.